Okay, so today we are going to talk about Dolbeault's lemma. So, in order to state Dolbeault's lemma, we need generalized Cauchy integral formula. And okay, so this is, I think, this is very easy in one variable uh, theorem. So we have D. It has the boundary gamma. I think in the book it is not mentioned that it must be anti-clockwise, oriented anti-clockwise, and f is going to be a function in a neighborhood. Let's say a neighborhood of this guy. So we have f. Uh, so we have a function defined in a neighborhood of this t. This is a c infinity function. So if it was holomorphic function, we must have this identity, but it is not. It is not uh, holomorphic. So actually, the correction with will be with this term, and well, the so the proof is not so difficult. Basically, what you do, you have your domain D, you have your gamma, you prefix Z inside your domain. You fix a very small disc. It's also uh, oriented anti-clockwise, and you start integrating. Let's say before this one, first you use. We will use this equality. So differential of this guy will be differentiation with the anti-holomorphic part because this it has already the zeta. So we just need to make derivation with respect to zeta bar, and at the end we will have this formula. And then the idea would be to apply now the Stokes formula. So the integration of we integrate this one over over this region, the complement, and we will have a by we will we will get this to this two integration because of one our let's say the boundaries, and then we have to take limit are equal to zero. Something that I didn't like in the Cunning book, the justification why this guy, let's say here, when r2 goes to zero, it converges. And for me, the reason is just because of this simple equality. That at the end you see that when you write in polar coordinates, the pole disappear. So you will have this one. So if you in this formula, uh, if you take r goes to zero, in one side you will have this one. This will be here, and the other side you will have, let's say, you have already we have already this one, and we have to justify that this guy when the when let's say when r goes to zero, this goes to 2 pi I fc. So the second proposition that we need in the proof of Dolbeault's lemma is this proposition. Okay, so it is basically again one variable context. Then we have this u, we have this k, and we have a function g defined. an open subset containing K, and and we want to solve this differential equation. This is the idea. This is there is G. Oh, the F is given, and we want to find G. In order to prove this proposition, the first trick is that we can assume that F is defined in the whole complex domain. So we have K, and we will take a partition of unity such that, well, similar, and in a similar way, in a partition of unity, we will take a function rho, which is as one in a neighborhood of this compact set. It starts changing, and after after a while, then it will become rho equal to zero, and and all this process will be at the end inside this U. So the idea is that if I make a row, multiply row with F, then it's I need to prove the same theorem for rho times F, and in this way I can assume that F is a C infinity function in the whole C. So once F is defined in the whole complex domain, so the formula for G is simply this one. And again, this for the same reason, this is convergent in Z, the same formula that we have seen in the previous formula. So and the verification is just computing. So let's just may to do the main steps. We make the derivation. Derivation will go. First, we will rewrite our integral in this format, and then the derivation will go inside. And after going inside, there is a very nice trick here that at the end, since this is fz plus zeta, then you change the derivation with respect to zeta bar because your function f is symmetric in z and zeta. And once you do this one, you write again your function in the let's say original format. And then in the last step, we have used this generalized Cauchy formula. Remember that for a very, very big disk, actually its boundary, this is actually going to be a disk, then f restricted to gamma is equal to 0. So that's why we will just have one part of the Cauchy integral formula, and the other one is just identically 0. So here we are ready to introduce our main theorem. So Dolbeault's lemma, and actually a version before the final version. So if we have two polydiscs, closed polydiscs, and we have a PQ form, it means that it had PDZ and QDZ bar. Phi in a neighborhood of big disk, big polydisk, and Q bigger than 0. And if it is if it is phi equals to 0, then this phi in this phi around the smaller polydiscs will be the bar of a dbar of some other differential bar. So this is the theorem that now we are going to discuss. So the proof of Dolbeault's theorem. So for the proof, basically how we started. So this is the trick. K, the smallest number, such that phi, the differential form, does not involve this dzk plus 1 bar until dzn. So the idea is that we will start try to prove this theorem from k0 until kn. And for k0, basically, uh, this phi will be automatically zero because we have assumed that our differential form has at least one dz. This is q bigger than zero. So anyway, for k equal to zero, there is nothing to prove. So we have to go from k minus one to k, and so until reaching the n, which is our main aim to reach. So once we assume that the hypothesis of our induction for k minus one, we want to prove it for k. So what we do, so in our phi, there will be dzk, uh, and and so there is no dzk plus one and dzn. Okay, and then we write our phi in this, we separate the part containing dz k bar, and so this beta does not contain dz k bar. So we make this separation, alpha, beta in a proper differential forms. And next we write alpha as as a usual Salom differential form. So there will be, let's say here, there will be, oops, just a moment. Uh, so we write our differential forms as sum. There will be p dz I bar here, and then there will be q times dz z. Oh, sorry, this doesn't have bar. This doesn't have bar, and this has a bar. Okay. Okay, so we start computing dbar phi. So dbar phi, when we compute it, and then we just substitute this one. At the end of the day, where we want to reach. Uh, so the point is that this guy has now has no dz cover, and this guy has no also dz cover. So there will be the first sum, there will g not equal to Kaval up here, because at the end there is already dz cover here, and yeah. So let's so so we will observe that this guy, for j bigger than k, uh, is this has to be zero, because my differential form has no dz plus bar war and so on. And remember that at the end of the day, we have this equality. So this guy has no dz plus bar 1 dz n bar, and in particular there is no such thing here. And the moral of the story is now that these guys will be holomorphic in this variable. So I g will be holomorphic in dz in zk plus 1 until zn. And something that also we will do uh, by the previous evolution that we, we, we introduced, we have to consider these functions. So maybe we will consider these functions, and in a neighborhood of this smaller polydisc P. And we will define the same things as alpha. So this is the expression of alpha instead of RIG. We have replaced this bigger, this capital RIG. So since RIG, RIG is holomorphic in this zk plus 1 Zn. The previous position, the previous proposition, the statement says that also this capital RIG will be also. Now the rest is just again computing dbar sigma. When we compute dbar sigma, we have to take care of this uh, derivation, and at the and just a moment. So we compute the bar sigma, and we divide it in three pieces. The one derivation with respect to z k bar, derivation with variables the j strictly less than k, and the one strictly less than j bigger than k. So one thing is that this term will disappear because all these guys are holomorphic in these variables, and at the end of the day we write our derivation in this format. And the main point is that now alpha and gamma, they just contain z1 bar until zk minus 1 bar, because we want to reach the hypothesis of our induction. They just involve this one, so they do not. This is minus 1, and so they do not involve these guys. And when we make phi minus d bar k, so this term will be cancelled. Then it will be just beta minus gamma, and so d bar of this beta minus gamma is equal to 0. So we use the hypothesis of our induction. So it will beta minus, it will be d bar of some zeta, and at the end we get what we wanted.